How does an impedance converter circuit work and how to design it? These are questions that are discussed in this video. As you can see, this circuit is implemented with two op-amps or operational amplifiers, and then we have five impedances up to five, Z1, Z2, Z3, Z4, Z5. What we want to show is the input impedance R in or Z in, as observed from perspective of this terminal with respect to ground, is equal to Z1, Z3, Z5 in numerator divided by Z2, Z4. Z2, Z4 being these two guys. So it's very interesting relationship. You would say, okay, what's the use case of this? Well, in this video, I'm going to quickly talk about why we need it, then how it works, and then I'm going to prove this quickly. If you are interested just seeing the proof, you can just, let's say, scroll to the mid video. All right, let's look at why. In many applications, realizing a large inductor, for example, is not possible. Let's say on the order of let's say 0.1 Henry, which is pretty large inductor. These are either very expensive, not possible, or even if they exist and you can purchase, they come with a lot of nonlinearity. Well, if we can, from perspective of input terminal, if effectively the circuit looks like, let's say, an inductor like this, a virtual inductor or simulated inductor between the input, let's say, node and the ground, or then we would refer to this as virtual inductor. It can be pretty large. We can effectively, if we can make the circuit stable, we can simulate as large as few henries of inductor, which is very interesting. So simulating inductors and virtual impedances is one application. Of course, it's possible to convert inductor to capacitor. So back to the inductor case, when I say simulating inductor, it means in the circuit, there is no inductor actually. So we only have capacitor and resistor in the circuit, and somehow the circuit will convert that into inductor. And this can be done vice versa. And it's just not limited to this. As a part of why, we can also realize a unique type of impedances from perspective of input. For example, we know that what inductor does is inductor in time domain take the derivative of the current and then multiply it by inductance to generate the voltage across inductor. So a current goes through it and a voltage across the inductor are related like this. Okay, what if, for example, there is a need for a very unique element that behaves like this? So we have, let's say, this current voltage relationship for this unique element. Let's refer to it as, I'm just making it up. Let's refer to it as, let's say, K. And let's say for this element, what we want is actually second derivative. So what the element does is it takes the second derivative of current, and then its voltage will be linearly proportional to second derivative. If we look at this element in Laplace domain rather than time domain, the voltage in Laplace domain across this element would be equal to K times S square times I square, the current that is going through the element. So neither capacitor nor inductor can do this. It's a unique element, but actually we can realize that with this circuit. That's the beauty of it. So with the proper selection of Z1, Z2, Z3, Z4, Z5, we are able to even generate or simulate these kind of a unique, interesting impedances. So that's about why. Now, how? Okay, so the way that the circuit works is interesting. You can see that effectively the wiring of the op-amp is in a way that we have negative, with the proper selection of component, we have negative dominant, negative feedback. So let's say, for example, if this node voltage goes up suddenly, what happens is, as a result of that voltage going up, op-amp senses that the input positive voltage, let's say if op-amp already at a steady state, but then suddenly voltage at positive terminal going up. As a result of that jump, assuming op-amp, let's say supply connected, then output, because noticing that positive terminal jumping up, would increase the output toward the maximum supply voltage. Then that means via this connection, the input negative terminal is also moved up. So basically it means that the negative terminal tries to catch up the positive terminal, indicating that we have the proper connection in terms of the negative feedback in the system. Another example is on this side as well. If we increase the voltage at the positive terminal suddenly, then op-amp notices that the positive terminal voltage is increasing, and then it would move or increase the output voltage to max, which is close to V supply. And as a result, there is a voltage divider across these Z4, Z5. If this node is increasing, the mid node is also increasing, and that means that the negative terminal start increasing as well. So see, the moment we have positive terminal jumping or increasing, then the circuit is wired in a way that the negative terminal also starts increasing. So that is the indication that we have proper wiring in the circuit and connection to terminals of op-amps. Okay, so now let's see. If when the circuit is in a steady state, we have op-amp 1 and 2. Let's say we apply a test voltage at input because Rin, which we want to find the formula for, which is proving this formula. So this Rin that we want to find it is obviously the test voltage that is applied at input divided by test current. If we apply a test voltage, let's say between input and ground, so I'm going to apply test voltage. That test voltage results a test current I flowing through the circuit, and if I can find V over I, that's the impedance, input impedance that I want to find and prove it is following this formula. So let's do that. In a steady state, because op-amps are properly biased, so the supply voltages are connected properly. Let's say let's say as an example, the 10 volt positive supply and 10 volt negative supply are applied. And then we have the proper feedback as discussed. So therefore, virtual short is valid for both op-amp, which means op-amp via feedback system is enforcing this property for input for the voltages of input terminal. So if I have V here, I have V here. If I have V here via this wire, I have V here as well. Again, for the second op-amp, for the same reason in terms of virtual short, we should have V here as well. So basically the input voltage V appears at all the 4 terminals of the 2 op-amps noted here. So then let's start. We have voltage V across the Z5 and ground. So there is a plus minus V across Z5. Therefore, I can easily compute this current, which can't go through the input of op-amp because it has zero, let's say, current that can go through because of input impedance of infinite. And therefore, there is a current I that is flowing this way and continues toward ground. And that current I can be computed as simple as this. Let's refer to it as, for now, just to avoid confusion, I1. Okay, so this current I1 can be computed this way if I change the color. So I1 is simply Z5 divided by voltage V across Z5 divided by Z5. So that's equation 1. All right, I'm gonna just continue here. So let me also remove this portion. So I am going to remove this portion so that we can have better conversation. So we still want to find out the why, how, and prove this. So why and how is done. We want to prove it. So proving this. All right, so we found equation 1. So what is the next move? Well, we have the voltage here, V. We have the current I1. So I can find the V out 2 at the output of the second op-amp because it is simply just a scale up of the series of Z5, the voltage across the series of Z5, Z4, because Z4 and Z5 are effectively in series. So what I can say, therefore, is V out 2 is equal to Z4 plus Z5 divided by Z5 times V, which is the voltage in the middle node, which is, as we expected, is 1 plus Z4 over Z5 times V. Okay, so that is V out 2. Okay, what's the use of this? Let's refer to this as equation 2. Well, I can just find then this node. I can find the current actually that is going this way. So this current, let's refer to I2, which is the same as this current. Reason for that is there is no current that can go this way because this way is going to two inputs, let's say positive terminal of op amp 2 and negative terminal of op amp 1, which both effectively have, each of them has zero current because of the practically infinite impedance that these inputs have. So then I2 is going to a series of Z3 and Z2. I can find it. How? Well, I have V here, and I also found V2, VO2. So that basically I have the voltage drop across Z3. So what I can say is I2 is the voltage drop across Z3 divided by Z3, which means V minus V out 2 divided by Z3. I'm going to substitute using equation 2. So using equation 2, therefore I can say V minus, so if I use this one, it is effectively V plus Z4 over Z5 V divided by Z3. So obviously these two cancel out each other, and what remains would be minus Z4 divided by Z3, Z5 times V. Interesting. So when you look at this outcome here, which I'm going to write it again here because it is useful, what I found is, let's say equation 3, the current I2 going through Z3 and Z2 is related to the voltage V at this node via the coefficient minus Z4 divided by Z3, Z5. That's a negative impedance converter. So effectively, if we were supposed to only look at, let's say, this portion of circuit, so I'm going to show it. If we were supposed to only look at this portion of circuit, like this, then this portion of circuit looks like exactly like a negative impedance converter, NIC. So the circuit that I'm showing is actually a more capable circuit than simple NIC. This is what the NIC is. When you apply voltage here, and let's say between that node and ground, then the sensed input impedance, Z in or R in, is exactly minus Z4 divided by Z3 over the other way. So it would be, because we are saying I equal to minus Z4 divided by Z3 divided by Z5 times V, hence V over I is minus Z3 Z5 divided by Z4, which means that the impedance observed at this node for the second op amp is actually can be a negative impedance. So effectively, the second stage is a NIC or negative impedance converter. It can realize negative impedance. It can be a negative inductor, negative capacitor, or even negative resistor, as far as we can make the circuit stable. So that's interesting. This circuit here effectively is a GIC or general impedance converter that can convert any impedance to any impedance effectively. Okay, so it's a good thing that we found this. Now, we found I2 in equation 3 as a function of the voltage V. What's the use case of that? Well, I can find, because of that, I can find V out 1 at the output of op amp 1. How? Well, we know that this node is V. So I'm going to write it here. So the voltage drop across Z2 is well known because obviously we have VO1 on one side and V on the other side. So all I need is then just finding the current I2, finding the voltage V out 1 by adding the voltage drop across Z2 and then to the voltage V on one side of Z2. So let's do that. So what I'm going to do is V out 1 is equal to voltage drop across Z2 as is shown here. And then we have plus V. So voltage drop across Z2 is just simply Z2 times I2 because that's the current going through Z2. And plus V, well, I2 then is what I can use from equation 3 as a function of V. So what I'm going to do is I'm going to say, okay, let's use equation 3 and to substitute I2 for I2, and then we get then minus Z2, Z4, Z3, Z5, V, and then plus V, which we can of course factor out V. And if you do that, then you end up with Z3, Z5 minus Z2, Z4 divided by Z3, Z5. And that would be what we found for Vout1. Let's refer to this as equation 4. The last equation we need is just going from, say, Vout1 to the input voltage. So now what I have, I already computed Vout1, that is equation 4. I know that input voltage is V, is the test voltage I applied. So effectively, I know the voltage drop across C1. All I need to do is finding this I current, which is the same thing as input current, because again, input current to positive terminal of op-amp is 0. So this I current can only go this way. Okay, so let's find it. The current I at input as a result of the applied test voltage is the test voltage V minus voltage at the output of op-amp 1. This is the voltage drop across impedance Z1. So therefore, I can say is over Z1, which means V minus, so using equation 4, I'm substituting for Vout1, because in equation 4 we found Vout1. So let's do that. So I'm going to substitute for Vout1, and I can factor out V as well. So it would be V over Z1. And then we have 1 minus, then as a result of factoring out, what we have is, or I can just multiply, it's fine with me. So let's factor out, that's fine. V minus Vout1 is just V minus Z3, Z5 minus Z2, Z4, these like this, and then Z3, Z5. Which if we compute that, then you can see that as a result of this final, let's say, equation, we have V over Zout1, and then times, we have Z2, Z4 divided by Z3, Z5. So that is I as a function of V. So the last thing I need to do is I need to just find the V as a function of I. So V over I becomes equal, just reshuffling things around, Z1, Z3, Z5 divided by Z2, Z4. Or you can write it this way, exactly as we needed to prove for, and this is R in obviously, V over I is what we refer to as the input impedance of this circuit, which we can also refer to it as Zn instead of R in. So we found the input impedance, R in or Zn, of this circuit. Let's keep it as it is. So V over I is R in is Z1, Z3, Z5, Z2, Z4. Okay, so we've proved the formula. Now let's configure the circuit. For example, I want to have, let's say, virtual inductance or simulated inductance at the input of the circuit. What can I do? Many possibilities. One example is, for example, let's say we can set, as an example, all we need to do is selection of Z2, Z4, one of them to be, let's say, a capacitor, so that it's inverted to an inductor by the circuit. For instance, in this scenario, what I can do is I can select, let's say Z4 to be a capacitor. So I can do that. I can just select Z4 to be a capacitor, this one. Let me use a different color. So if Z4 is a capacitor C, and if Z5 is a resistor, so I'm going to select, say, Z5 as a resistor, R. And then for Z3, I am going to select it to be a resistor as well. So effectively, I'm utilizing the inversion and also a negative impedance conversion. And then for Z2, I'm going to select as another resistor, R. And for Z1, let's say another resistor, R. So what is the thing I'm going to get in this case? Substitute for what we have, so we're going to get for R in, Z1 is R, Z3 is R, Z2 is, let's say, selected to be R as well. Hypothetical example. And Z4 is the capacitor, so impedance is 1 over CS. And finally, for Z5, we have also a resistor here, R. So what's going to happen? As you can see in this hypothetical example, R cancel out with, in this example, what happens is R cancel out with R, and what we're going to get is R square CS. So what is the benefit of this? Of course, we just realize a simulated inductor. So we can say that what we realize in this circuit is exactly L times S, because that's what is sensed or observed from perspective of input of the circuit. It's as if the input impedance is a constant, which is L equal to R square C. So by proper selection of a value of a capacitor and also reference resistor R, we can realize or simulate a virtual inductor or inductance at the input of the circuit with a value R squared times C, for instance. Again, there are many possibilities, but I just wanted to highlight the power of the general impedance converter or impedance converter as shown here, and the fact that, as I said, we will also be able to realize very interesting scenarios, like, for example, the second derivative, or let's say the kind of impedance that or kind of a component that computes the second derivative of the current and then reports it as the voltage across the component. So that's also interesting thing we can realize. You can even think of a weird scenario that we can compute or even report the third derivative, whether that's a practical or stable scenario, that's a different thing. But imagine that if we can, for instance, have Z2, Z4 as a capacitor, so that then they are inverted from denominator to numerator to report S squared. So if we have Z2 as 1 over CS, Z4 as 1 over CS, and imagine if we can have one of these three guys as an inductor LS, then effectively R in will be a cube function of, or basically a function of S cube. And function of S cube means computing the third derivative. So there are many possibilities that can be realized using this interesting circuit. I hope that this example is helpful in terms of highlighting how a GIC or impedance converter circuit can be designed and what are the benefits of that. Thanks for watching.